Hey everyone, and welcome to this explainer. Today, we are opening up a seriously crucial part of your developer's tool belt, and we're focusing entirely on linked list patterns. Now look, if you spent any time at all studying data structures, you already know that linked lists are incredibly simple in concept, right? They're literally just objects pointing to other objects. But when it actually comes to writing the code, man, they are notoriously tricky. They're kind of like the fragile glass pathways of computer science. One single miss null check, one pointer accidentally pointing out into the void, and your entire program just crashes to the ground. But honestly, don't worry, because mastering them isn't about memorizing syntax. It is entirely about recognizing a few repeatable, highly elegant patterns.
So, here is our roadmap for today. The structured tool belt we're going to build to help you absolutely conquer any linked list assessment. First, what is a linked list? Second, reversing the chain. Third, spotting the cycle. Fourth, finding the middle point. Fifth, the dummy node trick. And finally, number 6, your next interview step. Let's dive right in. All right, part 1. What is a linked list? The chain of nodes.
As a quick refresher, at its core, a linked list is quite literally just a chain of isolated nodes. Each node only holds its specific data and an arrow, a pointer, to the very next node in the sequence. That's the whole shebang. Now, because of this rigid structure, you don't get random access. You can't just magically ask for the 50th item like you easily can with an array. To find an element, it takes O of n time, meaning you might literally have to walk through every single node to find what you're looking for. But here's the massive trade-off. If you already know the exact position where you want to insert or delete a node, it is blazing fast. We're talking O of 1 time. You just break a single arrow, point it somewhere else, and boom, no massive data shifting required.
Now, to really lock this theory in, let's look at a real-life example. Think about a game. How do you navigate a scavenger hunt where each clue only reveals the location of the next clue? Well, you physically cannot skip ahead to clue number 5 without first finding clue 1, then clue 2, then 3, and then 4. That is a linked list in reality. You are absolutely bound to the chain, step by step by step.
Moving right along to part 2, reversing the chain, flipping the pointers.
Okay, so reversing a linked list is arguably the most famous computer science problem out there. But let's take it out of the code for a second and apply another real-life example. Practically speaking, how do you reverse the flow of traffic on a one-way street where cars only know the vehicle directly in front of them? I mean, if everyone suddenly tries to pull a U-turn at the exact same time, you're going to get a massive pileup. You have to do it systematically, car by car, making sure absolutely no one loses sight of the rest of the pack while they spin their vehicle around. Translating that back to our code, this delicate little dance requires 4 very strict steps. First, you must temporarily save the rest of the street so you don't lose it. Second, you flip the current car to face backward. Third, you step forward to the current car. And fourth, you move to the next car in the saved line. So the absolute crucial takeaway here is that you have to execute these exact 4 sequential actions over and over until you hit the end of the line. And when you do, your previous reference becomes your brand new starting head. It's beautiful once it clicks.
All right, part 3, spotting the cycle, Floyd's cycle detection.
So what happens if a node accidentally points back to a node earlier in the chain? Well, it's a disaster. Your program will walk that list forever in an infinite loop. To solve this terrifying problem, we use something called Floyd's cycle detection, which introduces 2 separate pointers. We use a slow pointer that moves just one single step at a time and a fast pointer that sprints ahead, moving 2 steps at a time. Let's apply our real-life question rule again here to make sense of this. If 2 runners, one fast, one slow, are on a track, how do you logically know if the track is a closed loop versus a straight line? Think about it. If it's a straight line, the fast runner will just disappear over the horizon and finish the race, never to be seen again. But if the track is a closed loop, the fast runner will eventually lap the slow runner from behind. They will inevitably collide. And that collision? That is your absolute mathematical proof that a cycle exists. Now, finding out a cycle exists is great and all, but how do we find exactly where the mistake happens? Where does the loop actually begin? Honestly, it's basically magic. Step 1, they meet, which proves the cycle. Step 2, you leave the fast pointer exactly where it is, but you reset the slow pointer all the way back to the head of the list. Step 3, you now move both pointers forward at the exact same speed, just one step at a time. Step 4, due to the actual mathematical distance they've traveled, the exact node where they crash into each other a second time is the exact node where the loop begins. Simply brilliant, right?
Let's hit part 4, finding the middle point, the halfway mark.
Okay, so we can actually recycle that exact same two-pointer technique we just learned for a completely different task. Here's our real-life scenario. If you have a digital playlist where songs only know the next track, how do you find the middle song without counting them all first? Remember, in a linked list, you don't inherently know how long the list is. Sure, you could count them all, divide by 2, and then walk the list a second time to find the middle, but that is incredibly inefficient. We really want to do this in one single pass.
The solution here is so elegant, it's crazy. If you send your fast pointer at double speed and your slow pointer at regular speed, the exact moment the fast pointer hits the final null node at the end of the list, your slow pointer has traveled exactly half the distance. Boom! You've just found the middle point in a single pass without ever needing to know the total count.
Which brings us to part 5, the dummy node trick, simplifying those annoying edge cases.
Listen, this is a design pattern that will literally save you hours of debugging headaches. Let's frame it with a real-life question. How do you organize a line of people when you don't know who will arrive first? Or worse, what if the person currently at the front of the line decides to suddenly leave? Who is the front now? If you are constantly shifting who the absolute head of the list is in your code, you're going to need tons of messy conditional statements just to handle the empty spaces.
So the crucial workaround here is the dummy node trick. You deliberately create a fake, empty node, a dummy, and you place it safely before the actual head of your list. It's basically like sticking a permanent, unmovable line starts here sign right at the front of your queue. Now, even if the actual head node gets deleted or modified or shifted around, your structure never breaks because the dummy is always securely holding on to the true start. When your code is totally finished running, you just return the element immediately following the dummy to hand back the finalized real list.
Let's look at how this builds a much larger solution, like if you needed to merge two already sorted lists, list A and list B. Merging them into a single sorted sequence is ridiculously easy if you use a dummy node. You start with your dummy, then you just compare the heads of list A and list B. Which is smaller? Well, 1 is smaller than 2, so you attach the 1 to your dummy. Then you compare 3 and 2. The 2 is smaller, so you attach that next. You just repeat this process, stitching the smaller node onto your chain until the whole thing is merged. Because of the dummy nodes sitting safely at the start, you never, ever have to worry about initializing the resulting list or dealing with weird, empty nulls. You just return the node after the dummy, and you are done.
Finally, we've reached part 6, your next interview step, the final challenge.
Okay, so we've officially built up your algorithmic tool belt with cycle detection, dummy nodes, and reversals. The source material we've been using for this explainer leave us with this stark, extremely direct piece of advice. Reverse a linked list without looking at notes. That's the one implementation interviewers ask for most. But why is that? Because taking that theoretical scavenger hunt, taking that one-way street analogy and executing it from pure memory proves that you truly, deeply understand pointer manipulation. It shows you aren't just reciting theory, you can actually manipulate the data in real time.
So I'm going to leave you with this final, ultimate challenge right now. Think back to earlier in the explainer. Close your eyes, picture that one-way street of cars. Can you mentally visualize those 4 distinct pointer steps? Can you actually trace the variables in your mind right now? If you can confidently write those 4 lines of code on a whiteboard without a second thought, you are absolutely ready. Thanks so much for joining me on this explainer. Now go out there and build something great.